So this is actually the second time making this video because, well, if Tim Cook, if you're watching this, your design for like starting the screen recording was dumb because you should have put that button for turning on the microphone without having to hold that stupid screen recording button for like 2 seconds, I think. Anyway, God forgive my angry soul at this point. But here goes the, we want to go over these problems, practice problems for Diels-Alder reactions that are on your page 49 of your wonderfully designed notes manual, unlike iOS 16 or whatever this is. So let's first take a look at this. And remember, for any Diels-Alder reaction, you should be concerned about two things: stereochemistry and regiochemistry, right? Maybe we'll first concern ourselves with regiochemistry first. And remember, that had to do with matching of partial negative charge with partial positive charge being bonded together. And then stereochemistry of Diels-Alder reaction is determined by the type of transition state. It goes through the endo transition state as opposed to exo. So that's what determines your product, right? So as for the regiochemistry, it's good to think about the resonance. So let's think about that here. If we do this resonance, which normally is not a good idea because we're creating a disparity in charges between the two of the same elements, carbon and carbon. So normally that's not a good thing, but you compared to doing the resonance at that bond, if you compare that to this other bond, right, hopefully you can imagine that this tertiary cation I drew here is better than having a secondary cation right there with the other possibility, for the resonance structure. So we could say that this is somewhat of a legitimate resonance structure. All of that to say, if you had to pick between the two carbons, either this or that, it's this carbon that has some partial negative charge. I hope that makes sense to you, because this acts as an electron donating group. Alkyl group, remember, is kind of a weak electron donating group. Things that have lone pairs of electrons that can formally donate a pi bond is usually a better electron donating group. Okay, so let's take a look at the other molecule, which is going to be our dienophile. I guess we could label this diene. And dienophile, remember, it's important to have an electron withdrawing group. I just want you to know that this is the dienophile alkene, and it has an appendage, which is this aldehyde, which is the electron withdrawing group. And remember, dienophile, it's advantageous for it for Diels-Alder reaction purpose if it has an electron withdrawing group, because you want to emphasize the LUMO, or the lowest unoccupied molecular orbital. So here's our electron withdrawing group, and this too has resonance, right? I guess we could have left that arrow there. So this would be one legitimate resonance, even though it's not going to be the major contributor, because it'll have sort of the unnecessary charge, especially on a primary carbon, which is not as ideal. But all of that tells us that there is indeed a partial positive charge on that end carbon. So what we need to do when we're figuring out the regiochemistry is to draw those two study materials in such a way that the partial negative charge and partial positive charge match up. Like this, right? As opposed to what you don't want to do is this, because the partial charges do not match up. Okay, so this is wrong. Okay, so once the reaction happens, like so, this is, by the way, just a transition state. It's not like an intermediate per se, because we just redrew the same molecules going through the endo transition state, which means that the aldehyde right here is right underneath the diene, as opposed to having the aldehyde sticking this way, right? If the aldehyde was sticking towards the outside, this way, then that would be the exo transition state, which we discussed does not take place in a Diels-Alder reaction. So the product should look like this. Now, this aldehyde could technically come from either the top face or the bottom face of the diene, so there should be a racemic mixture at this chiral center. So that's what I did there. Okay, so that's that first problem. And so just to emphasize the regioselectivity of this, I just want you to know that you should not be getting this product. This will not be formed. Okay. All right, let's think about this second problem. And this one's kind of an interesting one, because the diene is, of course, that. The dienophile is an alkyne right here, and I want you to know that alkynes, obviously, they have 2 pi bonds, so one of those can participate in a Diels-Alder reaction, just like alkene dienophiles that we've been seeing in our class so far. And we indeed have electron withdrawing group, so this does actually indeed make a good dienophile. So let's think about the resonance first to figure out the regiochemistry then. One thing I want you to note is bromine or halogens have those lone pairs of electrons, so if that moves around like so, you can get this resonance, which is pretty valid, because the bromine, though it has a positive charge, it still meets the octet. So this is actually not a bad resonance structure at all. So I want you to notice that there's going to be a partial negative charge on that end of the diene, not on the other end. Okay. Now, as opposed to like if you did this type of resonance, you might think you would end up with cation that's resonance stabilized, and that is indeed true, but remember, this too is resonance stabilized, right? So and this structure I just drew here is a secondary carbocation that does not meet the octet. So the original resonance structure I drew earlier, meaning this guy, is a better resonance. So we can be confident about the position of the partial negative charge. What about the dienophile? Well, let's think about maybe redraw. We're going to redraw this in such a way that we see all of the bonds. And we could imagine seeing a resonance like this, meaning there would be a partial positive charge on that end, terminal alkyne carbon. So all of that informs us that By the way, here I want you to notice I actually rotated around this bond like I did earlier as well with the first problem. And with this notation, my partial negative charge is right there, so I just have to make sure my alkyne should not be like this. That would be wrong. But my alkyne ester should be in this orientation, so that the partial positive goes with partial negative. And that will, after this transition state, remember that dagger sign means transition state. That would be the product. And notice that you end up with 2 double bonds in this case because we didn't use one of the pi bonds in this alkyne here. So that's what you see there. And of course the 2 new bonds are here and there, just like before. And there's no chiral center in this case because this normally would be a chiral center, but it's an sp2 carbon, so that's the only product. It's not even going to be racemic. Okay. All right. This next problem, let's think first about the regioselectivity, like all the other problems we've looked at. However, this furan, this is called furan, is symmetric, right? So there indeed very valid resonance that would put partial negative charge in here, but then you can draw the resonance in the other direction because it's symmetrical. So you have the equal amount of partial negative charge on either side of this furan, which means the orientation here really doesn't matter that much. So regioselectivity doesn't matter for this problem, but stereochemistry will, so we'll take a look at that. But just to be thorough, this dienophile, sulfone dienophile, it does have partial positive charge on that carbon because of that resonance. Okay, so now let's draw the diene, which is the furan. Right, furan is a diene, it's just that the 2 ends of the diene are connected through an oxygen. That's what furan is. And either side of this has a partial negative charge, so technically it doesn't matter which way our dienophile points to. However, stereochemistry matters, whether it's going to be exo. So exo would look like this orientation to react, where the electron withdrawing group here is not going to be right underneath or top of the diene. And remember, that does not happen because there's no helpful secondary overlap of molecular orbitals of the electron withdrawing group. So we should put the electron withdrawing group right underneath or top of the furan diene. So that's the orientation with which this reacts, okay? Even though it looks a little bit sterically congested or whatever, but molecular orbital overlapping and matching is a way more important factor than sterics in a reaction like this. So this happens. Remember, this is just a transition state. And I'm going to kind of draw the product in a kind of a newbie type of a way first, which Diels-Alder reaction always results in cyclohexene, right? The only thing is here the 2 ends of the cyclohexene is bridged by that oxygen right there. So that's that oxygen, right? And then this is the dienophile, or it was the dienophile alkene. And in the way I'm envisioning this enantiomer, right, like I had electron withdrawing sulfone group kind of tucked in underneath the furan. So I'm envisioning the enantiomer where the dienophile approached from the top face. And of course you can have a reaction product where the dienophile would have approached from the, did I say top face? I'm sorry, I meant bottom face of the furan is the product I drew here if the dienophile approached from the bottom face. If the dienophile approaches from the top face, then you get the other enantiomer. Now, I said that this drawing is kind of like newbie-ish, oops, but I'm going to try to draw it in a more professional way when it's a bicyclic system like that, which will look like this, and I have to say that looks really good. And then here's the sulfone pointing down and hydrogen pointing up, because there is indeed a hydrogen pointing up right there, right? And then of course the enantiomer, that's for the mirror image, that's the product, okay? And I still want you to see how even though it's bicyclic or whatever, that you still see this cyclohexene ring. And that's important to point out. It's a good segue for this next problem, because for D, we know what the product is of Diels-Alder reaction. We want to find out what the starting materials are. Okay. To figure that out, it's good to kind of think about the most fundamentally simple Diels-Alder reaction will be between this butadiene, and the ethylene. When this reaction happens, right, remember you gain 2 sigma bonds and lose 2 pi bonds, and these are the 2 new bonds. So if you need to go back to the starting material to figure out what they look like, you just need to identify those 2 new bonds that are being formed, which are going to be these 2 bonds. Hopefully you see this cyclohexene here. Right, that's the cyclohexene formed in the Diels-Alder reaction. Maybe we'll even write here that. Hold on one sec. I have. Sorry, I hope that video recording paused real quick. I just got a phone call from somebody trying to sell stuff to a company I used to be the president of that we never made money. But anyway, like it no longer exists. I'm surprised I still get a phone call about that. But what were we talking about here? So yeah, we were saying that the cyclohexene, is the hallmark Diels-Alder reaction. Okay, so that's good to note. And we do indeed see the cyclohexene, so we just need to unravel these 2 bonds, right? And we can kind of think about the mechanism in the reverse direction, kind of like this. Whoops, I made a mistake. It'll be like this, okay? That's kind of the reverse engineering of Diels-Alder reaction. So if you follow that, the dienophile will be this cyanoethylene, okay, that we've seen before, and then the diene will be, of course, a diene, but the 2 ends of the diene are bridged by nitrogen with methyl group and a methylene carbon, so that's the diene. Okay, just to clarify everything, I just want to show how the numberings would go. Like if we call this carbon number 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. That's the diene there. Okay, hope that makes sense. And it makes sense that this will be the product, because if you think about the resonance of this, right, like you can put a partial negative charge on this carbon, and then of course there's a partial positive charge on this carbon, so it should react in this orientation and not in this orientation. Right, hopefully that makes sense. So all right, the last problem is about the total. This is actually coming from a total synthesis of this very important natural product that I forgot to cite, which means this is kind of like plagiarism. But this molecule right here is called Taxol, or at least that's the commercial name. It goes by the chemical name paclitaxel, and it's one of the best-selling anti-cancer drugs even to this day. It inhibits the formation of microtubules, which are necessary for cell replication. And in its many-step synthesis, like 20 steps or something, but en route to this complex molecule, they actually used a Diels-Alder reaction where this was this intermediate, and then hopefully you can kind of find that same cyclohexene embedded in this Taxol molecule. So the question here is, what starting materials do you need to make this cyclohexene intermediate? And given that it's a cyclohexene, of course, this is going to be a good candidate to synthesize by Diels-Alder reaction. And like we said before, these are the two bonds that must be newly made in the Diels-Alder reaction, right? If you contrast that to this, okay? So what do we get if we sort of break those two sigma bonds and gain two pi bonds? The dienophile will be this, okay? So that is going to be, that's the dienophile. The diene of this molecule is going to be that. Okay. And the diene of this molecule is going to be this, and sorry, Kelly was knocking on my door. And so that's the diene portion, and if you just introduce the double bond here and there, that's the study material, right? So that would be it. So if you have any questions about this, it would be great if you can bring them to class, especially on this coming Wednesday. I'll see you in class, and please like